Let us start the first session. Do you hear me?
Yes. Yes.
Okay. The first talk, Juan Garcia Bellido, Primordial Black Holes. Please, 15 minutes plus 5 minutes for discussion.
Thank you, Sasha, and thank you, Jorge, and all the organizing committee for the invitation. I think it is a great opportunity to discuss with you these new ideas on primordial holes. So let me first share my screen, and then so do you see?
Yes.
The presentation? Okay. Right, I wish I could be there. Clearly what you have shown, Jorge, of an alloy is very attractive. So perhaps next time when the pandemic is over, we may be able to join all of you there in person and have discussions and collaborations with all of you. So I'm going to describe in the next few minutes what we have been working on for several decades already, but has given a tremendous boost recently due to the detection by LIGO and Virgo of binary black holes, which coalesce, and we observe this in gravitational waves. So since then, we realized that these black holes that we are seeing by LIGO perhaps have properties which are more appropriate of being primordial rather than stellar black holes from the evolution of out of supernovae, and possibly we may be able then to open a window into the early universe. So this is a great opportunity for fundamental physics to use gravitational wave detections to explore the early universe. As I will describe, these primordial black holes could have formed through the collapse of large fluctuations generated during inflation that re-enter in the radiation era, in particular in the QCD epoch, and produce black holes with a certain mass distribution, which then can be seen through many different, a very broad range of phenomena, a very rich phenomenology, which I will try to only show a very small glimpse of the whole picture. Obviously, those people that are more interested can follow my discussions with me and with others. Now, whether these primordial black holes are all of the dark matter or not, it's an issue which is still uncertain. We have to resolve this by having more observations. For the moment, they are consistent with being 100% of all dark matter, but only if they are clustered. They form pockets of primordial black holes from the early universe, and also they have a wide distribution. So the uniformly distributed black holes and just a single mass, what is called monochromatic spectrum of black holes, that one is completely ruled out, okay? But they could still be widely distributed, different mass ranges, and also clustered. Fortunately, thanks to LIGO, Virgo, and the future Kagra, and even further future, the Einstein telescope and other, and LISA, we might be able to measure with high accuracy the mass and the spin distribution of these black holes. Moreover, we not only use gravitational waves, we could also look for microlensing surveys to observe this mass distribution spin. Their properties have to do with clustering are best inferred from logical structure measurements, especially in the small scale logical structure. So that means dwarf spheroidals orbiting around the galaxy. And these will become very clearly visible in the next generation of surveys that will determine catalogs for the next decade and probably into the 2030s. So this is a summary. So let me go into the details. You're all familiar with the idea of inflation in the early universe, a very rapid growth of space-time and their fluctuations, whatever its origin. I'll describe a particular scenario, but whatever its origin, those quantum fluctuations are stretched to cosmological sizes, and we believe seed the structure. In particular, they seed temperature fluctuations that are observed already in the CMB. And they could give rise on small scales to features that may arise from some particular dynamics in the early universe. In particular, in this scenario that we put forward a few years ago, we use nothing but the standard model Higgs with a non-minimal coupling to drive inflation and have, if it's a critical Higgs, so if certain values of the parameters are satisfied in the standard model, we may have a minimum in the running of the self-coupling of the Higgs, and this provides a little plateau, if you can follow my cursor, where large fluctuations are generated, and these fluctuations give rise to primordial black holes, as you can see on very small scales. While on the very large scales, you still have the usual CMB anisotropies, which are proved by Planck. If you want, the primordial spectrum of fluctuations has a region where it is already tested by observations, both in the CMB and large scale structure, and another plateau at much smaller scales, higher wave numbers, amplitudes of order 10 to the minus 4 or so, where, as I will describe, we can then provide the necessary ingredient for the primordial collapse of gas in the radiation era to produce black holes. So there is a range of scales for which you could have a primordial black hole production due to this extra plateau on small scales. Now, the gravitational collapse, the physics of the gravitational collapse is well known. We understand this since the Penrose theorems, which received the recognition by the Nobel Committee this year. So any fluctuation which is sufficiently large above a certain threshold, here characterized by curvature fluctuation of order 1, will inevitably produce gradients, forces, which are stronger than radiation pressure, and therefore nothing could prevent collapse, as Penrose and later on Hawking demonstrated in their famous theorems. Now, if this happens in the early universe, in radiation epoch, then as long as those fluctuations, as long as you have a power spectrum with sufficiently large amplitude fluctuations, the tail of those distributions will provide the necessary seeds for the collapse of to form black holes. All of the mass within the horizon would form the black hole. And therefore, we have a one-to-one correspondence between the number of e-folds, the scale at which that fluctuation enters the horizon, and the mass within the horizon, and therefore the mass of the black hole. So the mass of the black hole is given in terms of solar masses, 30 solar masses for, say, a fluctuation that left 36 e-folds before the entry of inflation. Anything that left before, so 60, 50, 40 e-folds before the end of inflation would give rise to a much bigger black hole. Anything that left later on, closer to the end of inflation, of course, those fluctuations have smaller sizes, and therefore they enter earlier in the radiation era and have a smaller mass, a horizon smaller than that. Now, it's crucial here for the scenario to understand that this is very strongly dependent on the tails of the distribution. The probability of collapse, so how many of those domains actually do produce black holes, depends on those tails. And therefore, it's very sensitive to the non-Gaussian properties of those fluctuations. Now, we do measure in the CMB scales that the fluctuation is essentially Gaussian, so they are, the probability of collapse is essentially an error function, which is exponentially suppressed. However, having larger tails, and I'll describe in a minute our scenario, how that produces very large tails, you could have other statistics which are non-Gaussian, not highly suppressed. For instance, you could have chi-square statistics, which is just has an exponential tail, which gives you a large amplitude of large probability of collapse. So it's not so uncertain. What we thought 20 or 30 years ago is now more common. Now we understood that quantum diffusion, in particular in the stochastic delta n formalism developed several decades ago, we have a curvature fluctuation described as a fluctuation on the metric, space part of the metric, which can be described as a fluctuation over the number of e-folds of a given hypersurface, gives rise to a fluctuation amplitude which depends on diffusion, quantum diffusion. The field that drives inflation, in this case the Higgs, diffuses during inflation, can be described with Fokker-Planck diffusion equation, and we can solve this exactly using the finding the poles of the characteristic function and finding the tails of those of that distribution. We can see for potentials that are of the kind of the critical Higgs model with a quasi-inflection point, we can find high tails. That means high probability of collapse in the tail of the distribution. Rare events which would be exponentially suppressed in the case of a usual Gaussian fluctuation here are no longer suppressed and therefore may generate black holes much more copiously. You don't need a large amplitude of the power spectrum to produce a very large probability of collapse. Now, not only do you have fluctuations being much more probable to collapse to form black holes, but also there's a prediction that given that kind of scenario, the distribution is no longer monochromatic and uniformly distributed. The fact that you have high tails means that it's much more probable, these non-Gaussian features are much more probable to find a black hole to collapse near another one that has previously formed. And therefore, you would have larger black holes surrounded by smaller black holes forming clusters of black holes. So you have a range of masses and clusters of black holes where the most massive goes very quickly to the center through dynamical friction and smaller masses orbit around. So the new picture of primordial black holes is no longer monochromatic and uniformly distributed, which is what most of the constraints come through, but primordial black holes in clusters and broad mass distributed. This means that rather than being completely ruled out by observations, in particular by microlensing observations, the fact that they're clustered means that you allow for those constraints to dilute, essentially disappear. Essentially, you have much less probability of having one of those black holes between you and a star, which suffers microlensing. Other constraints from Planck, etc., also are diluted, and they leave precisely a window at the range explored by LIGO, around a solar mass to 100 solar masses. Now, what does that solar mass scale correspond to? Well, remember that fluctuations that are deep within the horizon during inflation and left the horizon some e-folds before have a one-to-one correspondence to the moment at which they re-enter. And this gives a scale. This gives both a length, size of the horizon, as well as a time, okay? This one-to-one correspondence means that we can associate, say, black holes that enter around the QCD epoch with fluctuations that left the horizon between 30 and 40 e-folds before the end, okay? Now, there's a whole range. You could go from the Electroweak scale down to Big Bang nucleosynthesis. All of those scales which re-enter could produce primordial black holes and still be perfectly compatible with what we observe. In particular, they could constitute a significant fraction of all the dark matter. And here's where we use the known physics, just like Gamow, when he extrapolated to the early universe the nuclear reactions for the early formation of elements, helium, lithium, etc. Here we can extrapolate the physics that we can explore with accelerators. It's no longer nuclear physics, it's particle physics. We can use the physics that we understand from, say, the LHC and reach, say, the Higgs scale of the top masses and ask ourselves, what is the rate of expansion of the universe at the time? How many relativistic degrees of freedom were there? Now, it's something very interesting that, as you all familiar with, as the universe expands, the temperature of the universe drops below certain thresholds, the thresholds of the masses of fundamental particles. At those moments, those particles become non-relativistic. They no longer contribute with radiation pressure to the plasma. So it is those periods where you have a sudden drop in the number of relativistic degrees of freedom, which has an enhancement. Remember that collapse, according to Penrose, collapse to form a black hole is very sensitive to the radiation pressure. So if you have a sudden drop in radiation pressure, the probability of collapse is exponentially enhanced. It's much more probable to probability. Now, there is a very sudden drop in the early universe when the QCD transition condenses hadrons and mesons. You had a plasma of gluons and quarks. They no longer contribute to radiation pressure when they form protons and neutrons, which are non-relativistic at formation. And then very quickly, that loss in radiation pressure produces a rapid decrement in the equation of state, or if you want, in the pressure in the fluid, and therefore higher probability of collapse. So there is a one-to-one correspondence, therefore, given a certain plateau with a given tilt, to have a large probability of finding black holes With what scale? Well, precisely that corresponding to the QCD scale. And this is 2 solar masses. So the main body of primordial black holes should have, we predict, a mass of a few solar masses. But that's not all. There is also, at the pion annihilation epoch, when pions disappear, they annihilate pi plus and pi minus, and they are relativistic, non-relativistic, sorry, they become non-relativistic. Again, there is a drop in, you can see in this dip, which produces a shoulder in the number of black holes, at say 1 in 100, of all the distribution of dark matter in the form of black holes. But there are also other peaks, those corresponding to the electroweak scale. And there are peaks corresponding to the time of a plus and minus annihilation, which correspond to 10 to the 6 or so solar masses. So these could contribute to the formation of galaxies much later on. They would be the seeds onto which gas would accrete to form accretion disk, the first galaxy, the first quasar. Now, masses around the electroweak epoch would give you a typical planetary masses. And these, there has been some observation from microlensing of black holes of those masses. So the whole picture is a very unified picture. We use early universe to describe the distribution of masses. And the question obviously is, are we seeing this mass distribution or not? As you can easily make the correspondence, the time at QCD is crucial because at that time, the absence of relativistic degrees of freedom produces a collapse, and this corresponds to a mass within the horizon, which can easily be converted into solar masses, which gives you essentially the Chandrasekhar mass. So it's maybe not so surprising that most of the primordial black holes, which constitute dark matter, have the masses of stars, which is a few solar masses to hundreds of solar masses. Now, something which is particularly interesting of this scenario is that you can use the QCD epoch to produce the baryon asymmetry of the universe. Unfortunately, I don't have much time in my presentation to discuss the details of these. Let me very briefly tell you that when primordial black holes form, there is a tremendous heating up of the plasma around the black hole. There's a shock wave. This produces enough energy to produce over the stellar transitions to generate the baryon asymmetry. At the QCD epoch, the CP violation is not suppressed, and you can produce baryons very near those black holes, which then diffuse out and fill the universe by 10 to the minus 2. 10 to the minus 2 seconds, much before Big Bang nucleosynthesis, you can dilute all of that. So the number of domains determines essentially the fraction of baryon to photons, which is surprisingly the same number, 10 to the minus 9. So 1 in a billion baryons to photons come from the number of domains that collapse to form black holes, if the black holes are all of the dark matter. So that's a very specific prediction of the scenario. So this means that we have opened up a new window into the early universe where primordial black hole as a dark matter in their collapse at the quark-hadron transition evolves producing baryogenesis, and much before nucleosynthesis, you have baryon dilution by 10 MeV, and you have generated all of the baryons at the time before a Big Bang nucleosynthesis ensues and you form the first nuclei. So that window is a window of opportunity for us to explore new physics and a new realm and solve many of the cosmological conundra that we have been in cosmology for, I would say, 100 years. But the true revolution came with the observations of gravitational waves from LIGO and Virgo. Now we have the GWTC2, the catalog of gravitational wave transient events from LIGO, which encompasses something like 100 black holes in 50 binaries. There is another 50 or so waiting in the second round, round 3B, which has not yet been published. But you see very clearly that the mass distribution, the vertical axis is mass in solar masses, is populated by very high masses, much larger than those that are expected from usual stellar evolution, which is around 10 solar masses. Whether these are primordial or not is an issue that we are exploring at the moment. But there are certain regions which are rather unexpected if they were coming from astrophysical black holes. In particular, there's the lower mass gap between 2 and 5 solar masses, and the upper mass gap between 50 and 130 solar masses. Those ranges were not expected to have any black holes and they are clearly seen by LIGO, both in the lower mass gap and the higher mass gap. I won't enter into details still. But let me emphasize that even though we're looking at these in gravitational waves at the moment, there are other sources in X-rays, in radio, from neutron stars, and also with microlensing. We can look with light, ordinary visible light, the light of stars, and look for the amplification of light due to microlensing. And already from OGLE, we have evidence of distribution of masses right in the range between 1 and even below 1 solar mass to tens of solar masses. Now this comes about because of the ability to use OGLE and Gaia to measure the positions of those lenses and determine from there their masses, break the degeneracy between the answer ring and the distance. And this gives a distribution, which are the red lines coming from Lukas Mirsikovsky and Ilya Mandel's paper, 2018, and superimpose their distribution, their likelihoods for the masses of those lenses, for microlensing, into the proton and pion plateau, proton peak and pion plateau from our scenario. And you see that it exactly coincides. Moreover, if you take into account GWTC2 together with GWTC1, together with the OGLE, they comprise the whole region of masses that are explored at the moment, between 1 and 100 solar masses. So we claim that most of these black holes, there might be a contribution that comes from stellar black holes. Most of these are primordial, especially the very high mass end and those at very low masses. Now, how come? We've seen that the masses coincide, but what about the rates? Is it possible that we can explain the rates having to do with primordial black holes that could constitute a significant fraction of all the dark matter? And for this, it's crucial that these black holes are clustered, because only there can you find the chances for those black holes to encounter each other and increase the rate. Otherwise, typical encounters of black holes in the galaxies are not sufficiently often to produce the range of masses, sorry, the range of events that will give rise to the events that have been observed by LIGO. So they have to encounter themselves there. But then most of these binaries, when they form, they are interactions with other objects, and they're thrown out. So they're thrown out as binaries. So they finally emerge outside the cluster. This is something that we realized very recently. Now, this allows us to make a prediction for what is the rate. And I'm finishing. I have 2 or 3 more transparencies. So let me postpone the question for later. So in this scenario, we can predict what is the rate of events in the mass range and the main component, MA and B. And we see that they all cluster with the sensitivity of GWTC1, so LIGO run 1 and run 2, they all cluster around this region. They're mostly centered around this peak, which has to do with the pion peak. Now, in run 3, and together with the others, a compilation of a GWTC2 of all the events up to the date, they precisely satisfy, they follow the distribution that we predicted. But there's an opening of a new island of opportunities. That is very large mass to light ratio, mass ratios, masses where one could be, say, 50 solar masses, the other one 10 solar masses or 5 solar masses. And these large mass ratios inhabits another island. And we claim that this will begin to be populated when you have enough resolution. It's clear that some events that have already been seen in run 3 comply with this new island, as well as these other events here. But that's not all. Not only do we know about their masses, the rates, but also their spins. Most of the LIGO black holes, I wouldn't say all, there are some that don't have this very small spin, but all seem to be consistent with all of those black holes which form the binary having initial spin equal to 0. If you have an initial spin, the projection of the spin on the angular momentum would still be 0, and this is where they cluster. Moreover, if they have initial spin 0, all of the final spin of the merged black hole, when they fuse, when they form a single one out of the emission of gravitational waves and the final merging, will inherit the angular momentum of the orbit. And then they have a very specific prediction for the spin of the final black hole, and that should be 0.68. And this is where it is seen most of the black holes are binaries are clustered around this final black hole spin. We did a much more detailed simulation with all of the events from run 1 and 2 and the 4 published events before October. And we found that indeed all of those black holes at to 90% confidence level are clustered below 0.2 or so 0.2 spin. So you don't have large spins for those black holes. Well, this is what we have at the moment. The future, before last transparency, the future is bright because we open a 3rd generation gravitational wave observatories, which will allow us to reach beyond the epoch of star formation, and therefore beyond the epoch of stellar black holes. If we keep on seeing black holes at that epoch, clearly they must be primordial. There are other ways, if you ask me, I can describe. But clearly, with the Einstein telescope and with LISA, we are going to explore those black holes up to redshift 10 to the 3 at the dark ages. Moreover, we are going to explore the below solar mass region. So we should be able to see black holes that could never have formed because of the Pauli exclusion principle of the Chandrasekhar mass limit below a solar mass. Therefore, if we see those, they are necessarily primordial. If we find a large contribution, then they are necessarily formed in the early universe. So let me conclude. Quantum diffusion inevitably generates primordial black holes, I have described during inflation. The thermal history then predicts that primordial black holes should have a multimodal mass distribution. We found peaks at 4 particular instances, 10 to the minus 5 solar masses, around 1, 2 solar masses, 100 solar masses, and 10 to the 5, 10 to the 6 solar masses. A question is whether there is another peak at 10 to the minus 10 solar masses, which could correspond, for instance, to physics beyond the standard model. So you see, we can use gravitational waves as a telescope for searching for beyond the standard model physics, which I find this fascinating. You can go back to the early universe with gravitational waves. Moreover, the predicted primordial black hole spin and mass distribution has already been measured, I claim, by LIGO and Virgo, as well as by Ogle microlensing experiments. And they find these black holes between 1 and 100 solar masses, which seem to follow the mass distribution of a peak coming from the proton epoch and a plateau coming from the pi annihilation. There are other peaks which could be explored with microlensing. I was mentioning 10 to the minus 5 and 10 to the minus 10 solar masses. The primordial black hole scenario resolves many of the very famous cosmic conundra. I didn't have time to go into those because of lack of time, but I'm happy to discuss this in the question session. It will open a completely new realm. It's a paradigm shift in terms of structure formation. The structure is formed by seeds of black holes, which then accrete gas and form larger and larger structures. On very large scales, it's not different from the usual collision-less dark matter. It's only on small scales that we should be able to see the difference. And it produces very rich phenomenology. It's a multi-scale, multi-epoch, and multi-probe problem, which we will be able to solve with future gravitational wave detectors, generation 3. And with this, I finish. Thank you very much for your attention. Are there any questions? I see some hands raised. I don't know whether maybe...
Alexander, you are muted. You are muted. Dr. Adriano, you are muted, so we can't hear what you're saying.
Should I moderate myself?
Sasha, are you there to moderate the questions?
You are muted, Dr. Adriano. You are muted. We cannot hear what you're saying.
That, if you like, I have a question, Juan.
I think Rafael raised his hand first.
I also have.
Sorry. Yes.
Nick and Rafael. I think that was the order. Nick and Rafael.
Ah, so is it me? Is it me now?
Okay.
Go ahead.
Okay.
As you like.
Yeah. Thanks. Very nice talk, Juan.
Thank you, Nick.
Yeah. One question. How long do you think is going to take until we know that the primordial black holes is not the whole of dark matter?
Excellent question. Okay, so the first thing, of course, is to determine that there are primordial black holes. And I think this will be pretty soon, okay? Clearly, it's possible that with the reanalysis of the time stream of LIGO and Virgo run 3, especially 3A and 3B, which have a bigger sensitivity, we might find within the noise these primordial black holes. And I would say that the best place to look is for large mass ratios. So black holes that have, say, in the binary, one with, say, 10, 15 solar masses, and another one with 0.5, 0.2 solar masses. These large mass ratios are difficult to search for. You're probably aware, you need very complicated templates, and they're difficult to find. However, and you need hundreds of millions of them, no, to look for the signature. But they would be deep inside the noise. You could extract, you could bring them over because they have many oscillations inside. So signal to noise ratio increases because of the many oscillations. Now, these large mass ratios might give you a sufficient liberum to see. Remember that the physical frequency, the one that tells you when the in spiral the chirp finishes, will be inside the LIGO band for these masses that I gave you. No, the problem is that, of course, very small mass for the companion would give you a small chirp mass, and that means that you are lower than the sensitivity. So you have to dig inside noise. Still, as I said, many oscillations will give you a larger signal-to-noise ratio, and eventually they should be seen. No? I know of 2 groups inside LIGO Virgo which are already searching for them. Right? So I expect that any time they will appear. If they are not seen in run 3, then we have to wait for run 4. And in run 4, most probably we will be able to see those. Now, one thing is to be for sure that there are primordial black holes. So if they're less than Chandrasekhar mass, they are not stellar. And another thing very different is to be sure that it's the whole of the dark matter. And for this, you have to be much more careful. You have to understand and make a relationship, follow very carefully the mass curve, disentangle the different populations, stellar from primordial, and then tell whether those rates of events that we observe for those that are primordial coincide with what you would expect from these clustered black holes that we have in our scenario. So this, together with absence of spin, would give you the third clue to determine their presence. Now, if you could use large structure on small scales, for instance, looking for dwarf spheroidals, which we are doing already with the Dark Energy Survey. I'm a member of the collaboration. No? And we soon will do with the LSST, Vera Rubin Observatory in Chile. So we will be able to tell whether through microlensing or through gravitational lensing, whether there are these clusters orbiting around our halo. Then immediately we'll tell those are primordial necessarily. They could not be dark matter clusters from particles. They have to be primordial black holes. And if you see, for instance, in lensing, you look for caustics, you would notice that around the cluster, there are some black holes that happen to be along the line of sight. This would give you an extra peak in the microlensing event. So there are many ways to search for and convince ourselves that this is at least comprises a significant fraction of all the dark matter.
Thank you. Thank you very much.
You're welcome.
Okay, next question, please. Rafael Bravo.
Okay. So Juan, thanks for your talk.
Thank you, Rafa.
So in the potential that you show at the beginning, this critical Higgs potential, right? The plateau that you showed corresponds to a neutron slow roll phase?
Not quite, because there is a slope. Let me go back to the...
It's just on a slow roll?
You can still have it in slow roll, yes. It's very steep just before. So at the plateau, you're in slow roll. It's not ultra slow roll.
Okay.
Let me go to the plateau.
That one.
Here, let me see. Actually, it's probably best to show here because this is the formalism we developed to understand what happens there. So quantum diffusion is dominant in this region. Okay, and this is what gives you these high tails, all right? Now, you notice that we don't need exactly flat plateau, which would give you ultra slow roll, maybe for 1 or 2 EFOLs. Here you have something like 10 EFOLs or so, where the field is being quantum diffused through this plateau, producing the high peak, producing this peak, this high plateau. Okay. This is produced by the diffusion. Now, you may see that here 10 to the -4, you would argue, well, that's not enough amplitude. Well, that's not true. What you need is this, the peak the power spectrum gives you the 2-point correlation function, right? While the tail contains the higher order correlations. And this is where you would have both the clustering as well as the probability of collapse on very small scales.
But the non-gaussianity is a necessary ingredient to produce the...
Absolutely necessary. Correct.
Absolutely necessary.
Without non-Gaussianities, without this exponential tail, there aren't enough black holes to form all of the dark matter.
You see, so if you don't have non-Gaussianity, you cannot produce primordial black holes.
Okay.
Right. Now, we have constraints from large scales, but not from small scales or non-Gaussianities.
Okay, thank you.
You're
okay,
welcome.
Thank you. Next question, Claudio Deep.
Yes, you mentioned that you can get baryogenesis at the QCD scale at some point, but I don't know where you get the CP violation in that case.
That's an excellent question. So most of the CP that we know comes from mesons, okay, B0, B0 bar, right? But this already tells us the VTB of the CKM matrix is order 1, right? And we know that there is a CP coefficient there.
Yeah.
Now, the point is, of course, we are suppressed by the Jaskov determinant. Now, the enhancement, it's a combination of 3 factors, as you know, through the usual Sakharov conditions. You have CP violation, which is not negligible, it's not 10 to the minus 20. If you are the QCD scale, you're not suppressed by powers of the masses, as you remember, that happens at the Electroweak scale. Then you need a baryon number violation. This you acquire because you heat up through collapse of the black hole. You have a shell of matter which is driven out and hits. It's like a fixed target experiment. It hits the surrounding plasma, which is at 70 MeV, but hits at energies of order TeV. This is enough to produce over the spheroid transitions. So you produce baryon asymmetry through a non-perturbative electroweak physics. And then you have the out of equilibrium situation, which obviously the collapse of black holes. If you do a careful computation of the modified Boltzmann equations in the presence of the shell out of equilibrium, and this requires careful simulations, similar to those that are done in first order phase transitions at the QCD epoch, when you have super quenched this new realization. You could have the Electroweak baryogenesis at the QCD epoch. Now, you have this super quenching. In the case of the primordial black holes, it's the shell of matter which is by conservation of linear momentum, which drives the heating up of the plasma around the black hole and over the barrier transitions. The CP violation on those particular CP violating interactions, which are not, so you're only populating certain modes, you're only populating the third generation, if you want convenience, you're not being suppressed by the small masses, are enough to produce the baryon asymmetry. And then you have to transfer the baryon asymmetry to the rest of the universe. But that's a different matter.
Yeah.
Okay, thank you, Juan.